Hello, welcome to our final unit on correlation and linear regression, which, put very simply, is lines of best fit, trying to figure out if our data that we've been given has some sort of relationship, no matter what the data is. So let's jump straight into an example. So this is an example from Khan Academy. You can see the link up top. Maybe I'll share that in the D2L. But the important thing is the table below, this table, shows the relationship between quiz scores and study time in hours for each student in Lucas's class, so just some boy. Plot the data in a scatter plot. So it just means plot the data so that these two types of pieces of information are related to each other, or they match up. So for a score of 17, so he studies for 1 hour and 1.75 hours, and the score is 17. So let's look for 1.75, score is 17. That'd go right here. And we're going to do that for the rest as well. So for 1.5 hours, he gets 15. For half an hour, he gets 7. For 3 hours, he gets 19. Just trying to be really careful here. And for 3.25 hours, he gets 20. 20. Come on, put it on the chart. And then for 2 hours, he gets 16. And our game that we're trying to play here, hopefully I didn't make any mistakes there, our game that we're trying to play is there a relationship between the amount of time that you study, so bigger on this x-axis, and the score that you get? Is one dependent on the other? And if I was to look at this, I would totally say that there is a relationship. And the whole point of this unit is to be able to figure out, are they related? What's the strength of this relationship between two types of data? And, you know, what does the data mean? Maybe we can just use these scatter plots to make predictions or understand our data better. So that's the whole point. Let's jump back into the notes. So the big ideas in this unit are going to be correlation, which means if there's a relationship between the two sets of data that we're checking, and linear regression, which is basically, essentially, lines of best fit. So if you were to take, for example, this data here, which is time studied and test scores, try to draw a line, maybe you would kind of eyeball it and say, this is maybe the line that you would make. It's actually probably not so good because there's a few pieces of data below it. But we're going to be able to figure out how to make Excel do the line for us, which will tell us if there's a relationship there or not. And we're going to be able to describe the strength of the relationship. So if you go down through the notes, the table of contents here should tell you exactly where everything is in the notes. So that's a good reference. Let's get into it. What is a correlation? Well, one way to explore what a correlation is maybe to understand what a correlation is not, or maybe what causation is and what causation is not. So for example, think about this. Does eating cheese cause people to get tangled in their bed sheets and die? Or does getting tangled in your bed sheets cause you to eat more cheese? Well, the answer is definitely no. But if you were to look at this graph, where the black line represents how often people get tangled in their bed sheets and die, and the red one being how much cheese they eat, you might want to say that there's a relationship here. So, yes, there is a relationship. There is a correlation, but that doesn't mean that one is causing the other. So the big takeaway here, and this is something you'll hear a lot if you ever do more stats, correlation, in other words, does not equal causation. One being related to the other, or going up together, for example, doesn't mean that it causes the other. So something important to keep in mind. Let's take a look at another one. If people fall into a pool and drown, does that cause Nicolas Cage to be in more movies? Or when Nicolas Cage appears in more movies, does that cause people to fall into pools and drown? Well, no, I don't think so. But if you look at this graph, it might suggest that they're going up together and coming down together. So does that mean that they are causing each other? No, but there is a correlation. There is a relationship between the data. It seems that one goes up when the other goes up, or one goes down when the other goes down. That doesn't mean that they are causing each other, but there is a correlation here. there is a correlation. And when things are correlated, it means that they go up and down together. And of course, statisticians and mathematicians, being the way that they are, they like to pick apart these numbers and pick apart this data and try to make sense of it with more numbers. So there's a nice, easy process for figuring out correlation. So first of all, correlation is a measure of strength of association between two variables. For example, eating cheese and getting tangled in your bed sheets and dying. It tells us how likely x and y are to move together, so the horizontal and the y and the vertical to move together, and whether they will move in the same direction or opposite direction. And if you look at all these, this is kind of our cheat sheet for what each of these things means. So for example, the correlation coefficient, which we'll talk about really soon, coefficient of correlation, or the correlation coefficient, is R, and all of these situations are dealing with R. For example, if there's a perfect positive correlation, that will be R equals 1, which means that they perfectly fit a straight line. Like you could take a ruler and your line of best fit would just be smack dab in the middle of all of those, okay? It would be a perfect positive correlation. Positive because it's going up. All of these would be positive. All of these would be negative, because their slope is going down. So you'll notice as the number goes smaller from 1, it gets less and less strong. You can still see a relationship, but it's kind of scattering out. It's not so strong as it used to be. In this 0 point, we've got a 0 correlation, which means we can't say that there's any relationship at all. And then as we go into the negatives, we again go back to -1, we get stronger and stronger, but it's in the negative direction, which means as one increases, the other decreases. So we'll talk a little bit more about correlation in this unit, of course. That's what most of this unit is about. But let's go back and just talk about the scatter diagrams that we've been looking at. So what is a scatter diagram, also known as a scatter plot? It just depends on who's teaching it and what textbook you're reading. Scatter plots. A scatter diagram, well, it has points to show the relationship between two sets of data. It's almost always two sets of data, although there are 3D scatter plots, which are kind of cool. They allow us to easily see the relationship between the two variables, and it has one independent and one dependent variable, which we'll break into in a second. In this case, dog weight and dog height, they are both kind of, there's no clear independent or dependent. But you can see that there's definitely a relationship here. You could probably draw a line through it. So there's probably a correlation between dog height and dog weight. Probably. We can say probably there is a correlation there. Independent and dependent variables are our terms for understanding or deciding which of the pieces of data are dependent on each other. Okay? So independent variable, the variable that is not influenced by anything, we put that on the x-axis. Okay, independent variable, almost always we put on the x-axis. It means that it's a piece of data that really doesn't depend on anything else. So for example, time or someone's age, well, time doesn't stop for anyone. Time is going to tick on by no matter what happens. But for example, someone's age, okay, also independent. But think of, I don't know, instead of thinking about time, think about the height of a tree. Maybe as time goes on, that tree grows higher and taller. So in a way, the height of the tree is dependent on the time. So what I was trying to say there is that time is going to tick on, that's independent, but lots of things depend on time. For example, time of a class, or the height of a tree, or things like that. So it can be called the input data. Dependent variable, on the other hand, is usually on the y-axis, the vertical axis. It's a variable that is affected by the independent variable. For example, a test score is dependent because it depends on how much you studied or slept or came to class. That can be called the output data. So we'll see here that the independent variable almost always on the x-axis, independent goes with the x-axis, and almost always the dependent goes with the y-axis. So while we're looking at this chart here, this chart, we don't know what the data is, but it could represent a lot of things. And we could say that this is a positive linear correlation. You don't need to know how strong that relationship is here to know that there's a relationship there, because that line of best fit goes up and to the right. So that means that as one goes up, the other goes up. So there's lots and lots and lots of examples of positive linear or positive linear correlations, which I'll explain a few in a second. So, for example, you might have more time running on a treadmill, more calories burned. More gasoline put in a car, the further it can go. As temperature goes up, you can sell more ice cream. As the tread on your car's tire gets smaller and smaller, the traction with the road also decreases, gets smaller and smaller. As the water levels lower in a fish tank, the volume of that habitat for the fish decreases. So all of those things are examples of positive linear correlations. There are also negative linear correlations, which would look like this. This would be negative linear correlation. So some examples of that are, a student who is absent for a lot of classes, high absences, decrease in grades. So high absence, low grades. Or if a chicken increases in age, the amount of eggs it produces decreases. So the bigger the age, the smaller the number of eggs produced. Or the older a man gets, the less hair they have. Or the temperature outside decreases a lot, so the heating bills increase. Or the more someone eats, the less hungry they are. These are all ideas that are negative linear correlations. And by the way, there's lots of other types of correlations. They're not always linear. We're just dealing with linear because it's the simplest case. So it's a good idea to start there. So let's do a few practice questions on independent and dependent variables. So in this example, the sales manager wants to know if there's a relationship between the number of sales calls made in a month and the number of photocopiers sold that month. The manager selects, little typo there, the manager selects a random sample of 10 representatives and determines the number of sales calls each representative made last month and the number of photocopiers sold. So this information is all given in this diagram here, or this table. So in this example, the independent variable it's telling us is the sales calls, and the dependent variable is the copiers sold. So take a moment to think about that and see if it makes sense. It's telling us the independent variable are sales calls, the dependent variable are the copiers sold. Well, that makes sense to me, because the more sales calls you make, the more copiers or printers you're going to sell. Sales calls, nothing really that we can tell is going to affect how many sales calls you can make, but for sure, the more sales calls you make, the more copiers are going to sell. And just by eyeballing this, it looks like this is about the relationship we have here. So that would be just picking apart one or the other. Let's try some smaller questions and see if we can figure them out. So for each statement, identify the independent variable, which would be like our x, and our dependent variable, which would be our y. So I recommend that you pause the video and, have a think about these for yourself before you watch me just go through the answers. So number 1, Mary goes shopping and purchases a bag of oranges. The oranges cost 5 Qatari Rial per kilogram. So I have a few questions that I left in from my time in Doha. I hope you don't mind. So that's just their currency. It's like $5. So Mary goes shopping and purchases a bag of oranges. The oranges cost 5 Qatari Rial per kilogram. Well, I would say that the independent variable in this case is the number of oranges bought, because you can just buy as many as you want, really. But the cost is the dependent. The cost is dependent on how many oranges you bought. Question 2. A scientist measures the height of a plant and counts the number of leaves. So in this case, the independent variable, I would say, is the height of the plant. But the way I tend to think about these is I try to figure out which one's the dependent first. So in this case, the number of leaves is the dependent, because the taller the plant, the more leaves you're going to get. It doesn't really make sense to say that the more leaves you have, the taller the tree is. The height doesn't depend on the leaves. The leaves depend on the height. So number 3, another question I kept in from Doha. Khalid puts petrol in his car and drives to Al Khor and back to Doha. He measures the amount of petrol left in his tank. So this one takes a little bit of thinking, and the question itself is not perfectly clear, but it seems to be he wants to measure the amount of petrol left based on how far he went. So this one, I would say the independent is the amount of petrol, or the amount of gasoline, and the dependent is the distance traveled. And you might disagree with that, and that's okay because this one's not clear. I mean, in this case, the amount of petrol, you put lots in. Of course, there's a limit, but let's just say we can put as much as we want. That's going to that's going to determine how much distance we can go. I mean, for example, I'll just make a little diagram here. If this is our petrol or gasoline, and this is our distance, the more petrol you put in, the more distance you can go. The less petrol you put in, the less distance you can go. But you could kind of flip that the other way too, couldn't you? The further the distance, the less petrol. So you'd have a whole different situation, really. So I'll just rewrite this. I'm not going to give you a load of unclear questions, but real-life situations obviously have some consequences like this. So this is the distance and the petrol. So the further you go, the less petrol you're going to have in the tank left. And then the shorter distance you go, the more petrol you'll have in the tank when you begin. So over time, your amount of petrol is going down. So it's hard to say exactly which one of these two cases it was trying to go with. I would say, just trying to decide which one I want to put my foot down for. Well, if he's measuring the amount of petrol left in his tank, that would be small over time. Let's say, for the sake of argument, that the dependent is the amount of petrol left in the tank. And the independent is the distance traveled. That one is tricky because of the way that it's set up, but I think that's what it's going for. The further you go, the less petrol there's going to be. But of course, that one has a situation where there's a bit of discussion there, which is normal when you're dealing with real-life data. It's sometimes hard to distinguish which one's which. So, in question 4, a study was done to find if different tire treads affect the braking distance of a car. So in this case, you've got your different treads. So your independent in this case would be your height of tread, I guess. Height of tire treads. And your dependent would be your braking distance. So the better the tread on the car, or the higher it is, the further you're going to be, or the faster you're going to be able to brake. We're not going to get into whether or not it's positive or negative right now. We're just going to label the variables. And for sure, the braking distance depends on the type of tires that you have. In number 5, students measured the temperature of the water at different depths in Lake Skywalker and found that the temperature varied. So the temperature is definitely dependent. So the dependent here is the temperature, because that temperature depends on the depth. The lower in the water you go, the colder it's going to get. We're not going to get into whether it's positive or negative, though, not right now. A researcher investigates the width of a river and the speed the water flows and found that there is a difference. So let's see, independent and dependent. So I like to think which ones depend on the other. Well, I would say that the speed of the water, speed of the flow, is dependent on the width of the river. And there are literally hundreds of examples you could come up with for this kind of thing, but if you can figure out which one's which, it'll help you a lot in the future. All right, let's move on to the next. So on the next page, we're getting into the nitty-gritty. We're getting into how to make a scatter diagram or scatter plot using Excel. Thankfully, Excel does most of the heavy lifting for us. So let's read the example. Toby and her friends deliver papers in Britain. They want to know if there's a correlation between how many days of the week they work and the number of papers they sell. Make a scatter plot of the data. Is there a correlation? So the first thing it asks us is, what are the independent and dependent variables? Well, I would say again, I like to think about which one's dependent first. Which one is affected by the other? I would say that the number of deliveries is affected by the day of the week. You know, the day of the week is not going to be affected by the number of deliveries. You could make 1,000,000 deliveries and it wouldn't change the day of the week. But the day of the week, if it's Friday or Saturday, it might make a big difference as to how many deliveries are being made. So that's my assumption here, is that these two things are the independent and dependent. And second, it says construct a scatter diagram in Excel. Now the steps are here, and you can read through them yourself. It says we need to put them in Excel. We need to highlight the columns, including the headings. We need to go to Insert, Line Graph, or usually we can even go to Recommended Charts. You can go to Scatterplot, and then we're going to change the header, give it some axes, and we'll be done. So let's pop over to Excel and do that. Okay, here we go. I've put the data into Excel. You can copy this and paste this from the PDF or the Word document, whichever one I've given you. And the important thing is that we can take our data and put it into the Scatterplot. So I'm just going to go ahead and select our data and Insert, and I'm going to go to Recommended Charts. You can also go to Scatterplot. So it makes no difference. I'll just show you. Under Recommended, it already suggests a Scatterplot, and it's looking pretty good already. So we can press that, and it says number of deliveries. Well, let's see, does that make sense? It's not clear here what our axes are, so we need to fix that. We want to add them in. So the easiest way is to right-click and go to Chart Elements here, press plus, and then you want some axis titles. So turn those on by clicking it, and then we can double-click and rename. So this is days of the week. Day of the week, we know that because we can see it's from 0 to 8, which matches up with our data. Our vertical is number of deliveries. So I'm just going to call it deliveries. We know it's the number of deliveries. And you can give it a catchy title if you want. Deliveries on days of the week. Or deliveries during the week. The title, as long as it's somewhat descriptive, that's okay. I'm going to make this a little bigger. And here we go. That's our scatter plot. That's all we really have been asked to do so far, so not too bad. We can clearly see that there is some sort of correlation here. So I'm going to click on this and copy, and I'm going to go back into my notes and paste them. So I'm back in the notes. This is the bottom of page 6, or page 6 after the instructions here. I've done everything pretty much that I needed to do. And it says, does it look like there's a correlation between the number of deliveries and the number of days worked each week? Well, I just look at the scatter plot, and you can say, yes, definitely there is. And I would say there's a positive correlation. And I say positive because positive is when it's going up like this. Negative would be down like this, which is not what I want, or not what I'm seeing. I can definitely see that there's some sort of relationship here. I'll work on making a good line of best fit soon. Alright, and that's all there is to it to make scatter plots. Let's dig into the strength of the correlation. So we talked about the correlation coefficient earlier. Remember, this is R. And R ranges from -1 to 1. And it can be equal to both. The negatives being how strong it is in the downward direction, the positives being how strong the relationship is in the positive direction. And everything you need to know is here. So a perfect correlation of R equals -1, the points are exactly on a line. As we make our way back to 0, it becomes kind of less and less negative. They spread out, spread out, spread out until there's no, like, you could draw a line like that, you could draw a line like this. Different students would have a lot of trouble trying to figure out what the correlation is. But as we creep our way back up into the positive ones, you can kind of make an effort and say, okay, maybe the line of best fit would look like this. Maybe, just maybe. And then, of course, R equals 1 is a perfect correlation. So you can see the different names that we use. I'll put these in a table soon. And then other cases, perfect positive, strong positive, weak positive, and so on. To break them down a little bit more specifically, we can use this table. I'll read about the information first. It says coefficient of correlation. Again, this is R. A number that shows a measure of the linear strength of the association between two variables. Let's just remember, this is correlation. Doesn't mean that they're causing each other. Causation. They're not the same. It ranges from -1 to 1, 1 being perfect, 0 being no correlation. It has a direction, positive or negative. Negative being this downhill from left to right. We also call positives direct relationships if they are going up in the same direction. As one gets bigger, the other gets bigger. The other one is called inverse. As one gets bigger, the other gets smaller. So as you go over, the other one goes down. If you put those two things together, what do you get? You get this. As one gets bigger this way, one goes down. So it goes downhill like this. And this is called our Pearson correlation coefficient. But all you need to really know is that these are the ranges that tell us our strengths. So it has a strength, weak to perfect. So from 0 to 0.2, plus or minus, it's basically negligible. We can't say that there's really a correlation there at all. As you creep up the line, anything from 0.2 to 0.4, it's weak, and so on. So this is what we will use to determine how strong our correlation is. And usually you want it to be at least 0.7. That would be kind of a good point. This and up is going to be strong, which means that there's a very good chance that your data is actually correlated. Let's do a few quick examples. So I recommend you pause the video and try this exercise for yourself. It says match the scatter plot with the correct correlation coefficients, and these are our 4 coefficients. So pause the video, see if you can try it. See if you can figure them out. Okay, I'm going to do the first one. Now to me, I can definitely see that it's positive. This is no question in my mind that's positive. But it's not perfect. It's just okay. So I would say it's positive, and I would even probably call it strong. So which one of these are positive and strong? Well, the first two are negative. 0 means none, so it's got to be 0.8. Let's try the next one. The next one is negative, and it's a perfect. Perfect and negative. So I should probably have said the negative first, just to be clear. It's definitely negative, and it's a perfect correlation. A perfect negative. -1. In the last, or in the third case here, down here, that is very difficult to know. Like some students might say it looks like this, some students might say it looks like this. It's very unclear what the correlation is, if anything. So I'm going to say it's either weak or probably negligible. Negligible meaning 0 correlation. It's just too tough to say. And without any tools like Excel to tell us otherwise, I'm just going to throw down 0 because that's our option. If you had to guess at this one, what would you say? Well, I would say for sure that it's pretty clear there's a negative going on here. So for sure that's a negative. And we only have one option left. It's -0.7. But you should say yourself it's still pretty strong going downhill. Probably strong or moderate if I had to guess. But because it gives us the option of -0.7, I don't want to confuse you by saying this moderate here. So I'm going to erase it. But you know, if you weren't given the -0.7, you'd want to think, okay, is it strong, is it moderate? And by the way, where I'm getting these words, strong, perfect, 0, or negligible, is from the table. So let's not forget about our nice little table there. All right, so that's it for this exercise. Let's see what else we have in store. So on the next page, page 9, it says, how do we write the correlation coefficient in terms of x and y? And it says the correlation coefficient of variables x and y can be written as correlation of x and y. So it's just a fancy way of writing it. All right. On Excel, a little bit of foreshadowing. On Excel, you're going to use this formula. equals correlation. You'll use your brackets, and it'll take your set of x and y values and tell you if there's a correlation there. So in the first example here, it says the correlation between x and y is 0.87, represents a strong positive or strong direct, I'll just put that in brackets, correlation. Remember, positive means direct, negative means indirect or inverse. So practice. What do the following values indicate? So once again, please pause the video to try this one, and then you can compare your answers to me. So number 1, correlation between x and y is negative 0.76. That would be a negative, well, let's start with the descriptor first. Negative 0.76, if I go up, negative 0.76 lives in this region, so that must be strong. So it's a strong negative. Strong negative correlation. Let's do the others. 0.12, well that lives, it's negligible. No correlation. If our data was to split that out, it would say no correlation. So I don't know. The chance of the sun shining if I flip heads on a coin, like no correlation. Number 3, negative 0.64. So 0.64 lives in the moderate zone. So moderate, negative correlation. 4, negative 1. That's a perfect negative. Perfect negative correlation. And 0.03 still lives in the weak to negligible. Even though it technically looks like it's not just 0, we still would not be able to negligible. We still would not be able to take it as a correlation. Basically, there's no correlation. We can't trust that. That could be just a little blip in the data. We don't know. So that's how you label these things. And so here are a few examples of those situations. In the first example here, 0 correlation. You can see all the numbers are just all spread out. Number of children versus annual income. There's no representation there in terms of figuring out a line. You could draw a line anyway through this and they would all work, right? In the second case, weak negative. So a weak negative correlation, you can see why, hopefully. They're scattered out, but they do have a general trend downhill. In the next one, strong positive. Not only are they going uphill, but they're all clustered around that line, as opposed to the previous weak case where they were not quite clustered, they were all spread out, but they were still giving the same story. And then all these situations, you know, high positive, strongly around that line of best fit, okay? Low positive, still uphill, but not so clustered around the line. No correlation in the third case. Low negative or weak negative, still downhill, but not so clustered around the line. And then high negative or strong negative, which would be close to the line. So the idea of this high positive, low positive, you know, this is, in other words, strong, weak, you know, weak, strong. They are just different words depending on different textbooks, but they all mean the same thing. How related are they? How closely clustered to a line of best fit are they? And finally, by the way, not all correlations are linear. You can have, you can have a smiley face correlation or all sorts of crazy correlations. They're not linear, but you could definitely draw a line through them. We're just not going to draw a line through them in this course. So it's possible at this point you're wondering, okay, well, we didn't do anything to do with the correlation coefficient when we did those previous questions. When I made my own Excel chart, we didn't do correlation coefficients. Well, now's the time for that. So let's use Excel to find the correlation coefficient. The function I'm going to use, I gave you a little foreshadowing earlier. It's this one right here. And now we're going to do the practice. So I've said open the Excel correlation and regression practice spreadsheet. That'll be on D2L. And let's do the first sheet called What's the Correlation? Okay, here we go. So try not to be too overwhelmed by the layout here. I just put all my Excel stuff here. This is the Excel correlation practice. And what's the correlation? And on the right side, I have our Pearson correlation coefficient table. I'm going to be using those to figure out what the strength is. So let's try it. Determine the correlation coefficients and describe the strength of their correlation. First question, number of tickets and cost. So for sure this is our independent, and cost is dependent on the number of tickets. So in order to get the correlation coefficient, I'm going to type equals CORREL. Look at that. Excel only has one that has anything to do with correlation. You can double click that. Array 1, that's my x values. If you're not sure, by the way, you can click this Inserts Function button and it will really describe what's going on. First range of values, blah, 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 blah. You can use it there. I'll just type them in. So equals correlation, double click. Array 1 is my x values, comma, y values. Close the bracket, enter. Ooh, 1. What does 1 mean? Perfect correlation. So perfect positive is what I would put in for that. And just to show you, I won't keep the graph, but just to show you that this is true, I'm going to do a scatter plot here, and we can see, hey, look at that. Actually, I can keep this. Why not? That's our first one there. Cost. Just a little tiny baby one, just to keep it there. That's our cost. All right, let's do the next one. Number of incorrect questions and exam score. So equals correlation, double click that, or just open the bracket. First array, comma, second array, so y values. Close bracket, enter. -1. So that's a perfect negative. So that's probably not the case for real world data. Although, yeah, perfect negative, of course it is. Because the number of questions, if they're all weighed the same, you will get that negative pattern going. So once again, I could make a little chart just to show you that that's true. And what do you know? This perfect negative. So that's our exam score. Neat. Okay, what about height and shoe size? So equals correlation, open the bracket, select your independent, and select your dependent. So the taller you are, you tend to have bigger shoes. Press enter. 0.9163. So that still means that there's a strong correlation. I would say very strong positive. Did I spell that right? Positive. Very strong positive. Not perfect, but pretty close. And if I was to graph it or to plot it, the scatter plot, you would see, yeah, pretty close. Not perfect, but enough to make a guess at the line. By the way, I'll get into this in more detail later, but there's a number of ways to add the trend line, one of them being here. You can see that, yeah, for sure there is some sort of correlation there, or at least there seems to be. So thinking about height and shoe size, I was thinking about this independent and dependent variable stuff that we had on page 3, and I realized I said that these are probably not clearly independent and dependent, but I changed my mind. The taller you are, the taller this dog is, the weight definitely is going to be dependent on that. The other way around really doesn't work. You're not going to get bigger and bigger and bigger in weight and get taller because of it. You get heavier because of the height. So that's just a little amendment there about what I said earlier. The dependent is definitely the weight, and the independent is definitely the height. So I'm sorry for making that small error in the beginning. So now we're looking at this question, test grades and absences. So let's see if there's a relationship there. So I actually do this sometimes with my own data, my own student data. Let's see if there's a correlation. By the way, there always is. Almost always. -0.9. So that also is a very strong negative correlation. Negative not meaning bad. Negative meaning that the bigger that the test grades get, the smaller the absences, or in other ways, the larger the absences, the smaller the test grade. So I'm just going to do a quick chart here. And we can see that the absences and the test grade, I would say that these are actually backwards, because the test grade is dependent on the absences. So how would you flip those? Well, the easiest way, or the most logical way, would be to switch the column order. So Excel assumes, I just copied and pasted there, Excel assumes that, I should keep all of them, sorry. What am I trying to say here? One second, can't do two things at once. Okay, Excel assumes that your leftmost column is going to be your X and your rightmost is going to be your Y. So if you notice that the dependent and independent are something to be aware of, or there's something weird going on there, then you should seek to remedy it. So correlation, this is really the dependent, the absences, the independent, and the test grades are dependent on those. So basically the same, that might even be the same number as I had before, but the important thing is that the plot's going to look slightly different. It's going to be more easy to understand because your absences now are on the x-axis and your test grade is on the y-axis. I hope I didn't throw you off there. I was just trying to make it more clear. This was the original stuff. I just switched the order so that the chart would make more sense when I graphed it. There are other ways to switch the position like that, but I just showed you one way. So this is what? This is a negative, and definitely very strong negative. Okay, now let's do the last one. IQ score and height. I have a feeling it's hard to say which one's dependent or independent, so I won't even bother to worry about it. I'm just going to figure out if there's a correlation. First column, second column. 0.3. 0.3 is a weak. So a positive weak, or a weak positive. It doesn't really matter which way you say it. I'll say weak positive. And there we go. This situation, if I was to graph it, you can see that there's a relationship here, maybe. Sorry, I don't have enough space going on. There's a relationship here, maybe. There's a general trend that they're increasing together, but it's a pretty weak one. And if you just click on trend line, you can see Excel tries to match it, but they're so far away from that line that it would be hard to make that argument that they're related. Like, you'd have to really dig into the data and convince someone that they're related. All right, well, that's how you do scatter plots in Excel. We only have a little bit left to do, which is doing the full sort of chart. So let's do that, and we'll be done this unit. Okay, this is page 9 in your notes. Page 10. Sorry, page 10 back in your notes. Regression line. So the functions in Excel we're going to use are correlation, slope, and intercept. Correlation, slope, and intercept. But let's get into why we'd use those. Linear regression refers to a way to make a straight line relationship between two variables. A regression line is a single line that best fits the data. So it's the line that we've already been working with. It's the line that tries to go through the data the best that it can, and some of the points will be right on it, and they'll be spread out about that line. So the idea here is that if we have two pieces of data, for example, weight and height of someone, and you plot them, and you see that there's possibly a relationship there, a correlation, then you're going to want to go ahead and work on that line, that best fit line, to see how strong the relationship is. So it's most common to calculate a regression line for two variables when first their scatter plot looks like a line, or close to one, and two, their correlation between the variables is strong. For example, R is 9. So that's what I did in my Excel example. In the Excel example, let's see if I have it. Okay, here we go. So yeah, we didn't know much about the data. We couldn't see the data, but we had our correlation coefficient. We talked about the strength, and then I made the graph because I saw that the correlation was pretty high. So that's the situation you would use to figure this stuff out. So the scatter plot looks like a line, or the correlation between the variables is strong. We usually make the regression lines using Excel. You wouldn't want to do it by hand. It would be kind of an outdated method. And they have a standard equation, which you might recognize from math class. Y equals mx plus b. And it has three pieces. Your y hat, or y, is the average predicted value of y for any x. B is the y-intercept, where it crosses the y line. But even more importantly, m is the slope of the line. This is not r. So many students say that the slope of the line is the correlation coefficient. That's not true. That's just the slope of the line. It just tells us if it's positive or negative. Okay, so Excel is going to be able to do this stuff for us, but let's actually dig into the equations for the lines to see how the regression lines can help us predict things or understand our data. So regression lines and examples, regression line examples in practice. Example, we are told that the relationship between the profit a movie makes in millions of US dollars and the number of theaters, T, showing the movie is given by this relationship here. How much would a movie make if there's 350 theaters showing it? So theaters here are T, so if T is 350 and Excel gave us that regression line, we would be able to figure this out quickly. You would take your values, put in your T, and figure out what the prediction is for 350 theaters showing the movie. And when I do this, I get 1.9021. That's 1.09021 million US dollars. So we don't know what the data looks like. We just know that this equation was found somehow, and then we can predict how much we can make given this equation. So notice that the predicted value is, this would be our slope, this would be our x, and this would be our y-intercept. And if you want to see what this looks like, let me just pop it up on Desmos so I can show you what the line looks like. Okay, so I just tossed this into Desmos, I put the equation in there, you don't need to worry about that. You can see that the y-intercept is indeed at negative 1.668, and at 350, if you make have 350 theaters showing this movie, the value it gives is 1.902. So we can predict different amounts of money we'll make based on the equation alone. So let's go back into the questions. How much would a movie make if 862, so you'd do the same thing, 862, and then you would figure that out. So once again, same idea. And this gives us 7.1245 million US dollars. Alright, so I'm not going to get too much into this. That's just how the equations work. It's just a preview into how we'll use our equations. How many theaters would need to show the movie in order for it to make $3,500,000? So in this case, if our profit is in millions, this would be 3.5 million. So what you would do is use your equation and say 3.5 equals 0.0102 t minus 1.6679. And you would solve for that t, and then just using the equation alone, we could figure out how many theaters we would need to show it in. So the answer for this is some basic rearrangement. I guess I could make it more clear. So 3.5 plus 1.6679 equals this. Simplify the left side. It should be this. And then I'm going to divide both sides by 0.0102 to get my t. Which, if I haven't made any silly mistakes, is 506.66 theaters. Or, you can only have a theater or not. So I'm going to round to the nearest whole. So there we go. 507 theaters. So long story short, we were given our regression equation, which was given as a simple linear equation here, y equals mx plus b form, and using that you can find x or y, or in this case, T, or P. So the practice here, I'm going to leave that for you to try. The basic structure is exactly the same. So you can give that a shot for extra practice, but I'd like to do a few questions in Excel. So examples in practice in Excel. It says open the Excel correlation and regression practice spreadsheet, complete the study hours, dexterity, and brain and IQ sheets. So let's get to it. But before I do that, I'll do the last real thing that I'm going to get into for this topic. What's the relationship between correlation and linear regression? Well, the closer the correlation coefficient is to plus or minus 1, the closer the data points are to the regression line. For example, a correlation coefficient of 1 indicates all points would be on the regression line. And the fewer, let's see, the fewer points that are on the regression line, like in this case, the further and further away that's going to be from r equals 1. Sorry to jump back and forth here. Finally, when the correlation between x and y is significant, for example, r is close to plus or minus 1, the equation on the regression line can then be used to predict the y values for certain x values. But be careful. Prediction values are usually only meaningful for x values near the observed x values in the data, which means, like, if you've got your chart, I probably don't need that to be blue, you've got your chart and you've got all your points around here. Let's just say this is your points, this is your regression line. You probably don't want to wonder about a point out here, because a lot can change from these boundaries up to that point. So what I'm trying to say is try not to extrapolate. Too far. If you extrapolate too far, then you're making predictions that really aren't based on real-world data. Okay, so now that I've done that, the last thing I'll say before I go to the Excel is this last section here. Okay, it says how to make a regression line in Excel. You can read through that. That'll explain the method I'm going to use. And finally, this method of least squares. We're not covering this in class. You can read this page and watch this video, but I'm not going to ask you any questions using this method for calculating, okay? So there are examples here, but for reasons such as COVID, we're not going to get to them. So, long story short, let's do those examples in practice in Excel, and we'll be done. Okay, here we go. This is the Excel practice, and the last thing we're going to do. So I already did where's the correlation. Study hours and brain IQ I'm going to leave for you. Those are going to have their answers online. You should check those out. I'll go through the dexterity problem. So in this case, the following data is from a group of 11 students. The X value represents the number of alcoholic beverages consumed, so down here, and the Y value represents their scores on a dexterity test. And we want to know that if drinking alcohol can affect your dexterity. And guess what? I bet the answer is yes. So let's do this. First of all, we need our correlation coefficient. That would be R, right? So I'm going to use correlation. And I'm going to use my X values, comma, my Y values. All right, negative 0.97. So to me, that looks like a pretty good indicator of a correlation. In fact, a very good one. The strength would be very strong. The type of correlation, in this case, would be negative linear. It's negative because, you know, we've got our negative up here. You can see it right there at the start of the correlation coefficient. And it says to explain the relationship. So can you explain what's happening here? Can you use this idea of negative linear to explain to someone what's going on between these two things in plain English? So by me looking at this, I see that as the beverages go up, the dexterity goes down. So I would say, based on my data, as alcoholic beverages or beverage intake increases, dexterity score decreases. The slope. What's the slope? Well, we can figure that out by using equations. We can also find the regression equation another way, and I'll go back to that in a second. But let's just say you only knew the Excel formula, equals slope. I'll click that. What does it say? Known y's and known x's. Okay, my known y's first. That's these. comma, my known x's. That's these. So be careful, they're backwards. The slope of the line is going to be negative 9.7. That's our m value. Our y-intercept, what's the formula for that? It's intercept. It's already there. Known y's and known x's. Y's, x's. That's our y-intercept. So based on that, what is our regression equation? Can you make it based on the slope and the y-intercept? Well, yeah, you can. Not too bad, actually. Not too difficultly. Because the regression equation, remember, is y, I'll put this down here, y equals mx plus b is our format. So y equals our m, so negative 9.7 we'll say. We'll just round it because all of these don't have any decimals. I'll round to the nearest decimal. So I probably should have rounded those off as well. That's okay. X plus 102. 102. Mx plus b. M, x is general, plus b. There we go. So before we go any further, I just want to make sure you understand what the slope and the y-intercept and everything means. The slope, remember, just like our regular equations, is like rise over run. So in this case, what we're going to have is our dexterity per beverage drink. Okay? So for every one beverage we drink, the score will decrease by 9.7. By the way, if you want to fix these decimals, you can change their format. So right-click, Format Cells. You're going to tell it it's a number, and if you want 3 decimal places, for example, you can click 3 decimal places and press OK. For slope, it's probably enough to give 2 decimal places, or even 1 decimal place. And for y-intercept, it's also definitely enough to do 1 decimal place. So that'll clean up our data a lot. For our second situation, our y-intercept, what does the y-intercept mean? Well, it means that when we haven't drank a single beverage, that's our dexterity score on average. So the regression equation shows a dexterity of 102 with no beverages drank. And what does our regression formula mean here? Let me space it out a little bit. It means that our dexterity is negative 9.7 times our beverages drank plus 102. So I'll write that more clearly for you. Dexterity, negative 9.7 multiplied by whatever beverages drank plus 1 over 2. All of this will make a little more sense in a second. Let's make the graph. So I'm going to select my data, insert. You can choose recommended charts or scatterplots. Recommended charts will have it there, and Scatterplot will have it there as well. I'm going to put that in the space for the graph. You can see that there's definitely going to be some sort of relationship here. So we can add the trend line to this graph. Just click on the chart area, add. First of all, we want to add our titles. We're going to want to add our trend line. I'll do my trend line after. So click on axis title. This is my y-axis, which is going to be my dexterity score. Dexterity test score. The bottom axis title. Oops. Sometimes Excel is a bit finicky. Bottom one, number of alcoholic beverages consumed. Yep. My title, give it something a little bit more title-y or more catchy if you want. So, lay off the drinks. And what are we missing? We're missing the trend line. So you can click on it, go back to addition, click trend line. That'll give us the general. That's not quite enough. I want the full experience. So go to more options, go all the way down to the bottom, and you can say display equation on chart. So what this gives us is our equation, and you'll see it matches up. Look at that. Matches up perfectly. And it also gives us the r squared value. The r squared value is literally our r squared. So if r squared is 0.9592, then our r is the square root of that. Okay? Squirt. Square root of that. Oops. Shouldn't be 0. I know what I did. I typed it in the one cell by accident. So I'll take that out there, put it in here. So 0.9592. I want the square root of that. Okay, so you'll see that again it matches up. I don't recommend that method for getting R, so maybe just forget that I did that, but at least you can know that that's one way to do it. So let's see if we've accomplished everything we want. We've got our chart there with all of our data. We can see that it is definitely a negative. It's strong, negative linear. Our equation is right there for us. We could even just pick out slope and intercept from that. And now we can make some predictions if we wanted to. By the way, if you wanted to change the design here, you don't want to go through all that extra work of putting all the trend line in. Quick layout 9 will give you all that stuff. You would just need to delete the extra stuff. So it's up to you how you want to accomplish this. Prediction. If drank 12 drinks, what is score? Well, if I drank 12 drinks, it's outside the scope of my data. I can't predict it. It's outside of my scope. It's not, it'll go past 0. Like you can see it's too far there from my trend line. I can't predict if it's 12. But I can predict if I drank 3 drinks, what's the score? So I'm going to give it, use my formula, equals negative 9.7, and I'm going to multiply it by my slope. Sorry, I'm going to multiply it by 3, and I'm going to add 102, and it'll be 72.9. I can show you that another way. Remember that it's y equals mx plus b, so equals, y equals, our m is my slope, multiplied by 3, given in the question, plus my b value, which is my y-intercept. It gives me the same thing. You might just want to tidy that up and make it 1 decimal place. And that's how you handle these questions. Hopefully that wasn't too much all in one place. I was trying to keep it brief, but also not go too fast. If you have any questions for me, it's very important that you get in contact, okay? But that's it. Study hours and brain IQ I'll leave for you. I'll put the full answer keys online. And then remember that the rest of these notes, first of all, is just how to do the regression lines. And then a little bit about a topic that we're not going to do. So congratulations if you made it to the end of this video. That means that you've finished the content for this course. Pat yourself on the back and start getting ready for the final exams. All right, take care, everybody. It's been a pleasure.